In my last two videos, I showed how I began work on the horizontal sync board of a Ben Eater style video card. And then I showed how to use this divide by N circuit that I built along with a Ben Eater, slightly modified Ben Eater clock circuit to check the values that I'm measuring against, the 200 and 242 and so forth, for the various signals for the horizontal sync board. So here I've completed the board, and I showed you how I used that divide by N to check on the 200, 210, 242, and 264 values that are supposed to be measured by these four 8-input NAND gates chips. Since then, I have built the vertical sync portion. If you'll remember, in one of my videos, one of my viewers was concerned that the CD74 HCT 4040 chip is not a synchronous counter. It is what's called a ripple counter, meaning that the bits don't all flip exactly at the same time. So we measured some signals on the counter to see what the delay would be, to see if we thought it would be a problem. And I came to the conclusion that it should work fine. So since then, I finished building the circuit. So this is basically a Ben Eater video card, except that instead of using 74161 4-bit counters, I'm using just a single 12-bit counter. And that allows me to compress the size of the board card down to 3 boards. Another difference I'm doing, just a small one, is I'm using this zero insertion force socket to make it easier to load and unload my ROM chip. And these allow you to just drop a chip in, and then this lever, you can lock it into place. A downside is that it's quite a bit wider than the actual ROM chip. So there's only sockets for one row of socket on one side and 2 rows of sockets on the other side. And that does make the wiring a little bit more fraught. But I was able to wire it up just fine and get it to work. To check it, I'm actually not using a VGA monitor. I'm using this VGA capture card that I ordered off Amazon. And let me just give you links a minute for those. So if I switch to this tab, you can see this is the 40-pin universal 0 and 4 socket that I'm using. You can see you can buy 5 of them for $8, so they're pretty cheap. It's worthwhile investment. I will say another downside of that, not only the width, but also this is a 40-pin socket, and you don't really need 40 pins for the ROM chip. You only need 28, or for the chips I'm using, I'll show you, I need 32. But anyways, it does use up a bit more breadboard space than if you just plug the chip in directly to your breadboard. And this is the link for the VGA capture card that I ordered. If you wanted to do what I'm doing, you can do that. You can then just look at this capture card using a VLC, which we'll see in a minute. So going back to the video, here I can show you that it works. So I'm going to plug in. Now this is, I'm actually not using ROM chips. It turns out that the you can find 8K ROM chips pretty well, but the 32K ROM chips, the AT 28, was it the 28 AT 28 SF 256 chips are really hard to find. I couldn't find any at Mouser or DigiKey or Jameco, which seems to Jameco doesn't seem to be carrying them at all anymore. So this is an SST 39 SF 010A, and this chip is a flash RAM chip, but you can program it with an EEPROM programmer, just like you can an EEPROM. And it does have an advantage that it is slightly faster. So I don't know if you can see right here, that 70 right there. That means that it is it responds in 70 nanoseconds. So the 28 series EEPROMs respond in 150 nanoseconds. So this is more than twice as fast, and that can be helpful. So this is a 1 megabit or 128 kilobyte chip, and it does have 4 additional pins, making it a longer chip. So that is a disadvantage. If you're a real purist, this chip is not the technology that would have been available back in the late 70s and 80s when this kind of technology that we're talking about was invented. So if you're a purist, then this chip is cheating. But I like them a lot. It's them quite a bit. So let me lock that into place, and let me wire up my vertical sync. And I am, these are wired up exactly the way Meter did his. I'm ground, red, green, and blue. These are 1.5K resistors and 680K resistors, so we get the same color palette that VGA card uses. Let me plug in the power. And let's take a look. VLC, and there it is. How I got this was media, open capture device, and I just select the video capture device that was created by that VGA capture card that I showed you, and click play. And there's the card. Now this is the binary image that I downloaded right off Ben Eater's website. So this is exactly his image. Now, if you remember, Ben Eater created this image by downloading an image of a Goldien finch that was free for use off Google, and then he put that image into Photoshop and converted it to a 100 by 75 image, and he cropped it slightly because it wanted 75. The way the image was aspect ratio was, it would have been 114 by 75, so he cropped it down to 100 by 75. And then he applied a color map, which he was very clear to say that you had to have the colors in the color map in the exact right order, but he did not explain how to get that order, nor did he explain what Photoshop does to reduce the color of the image then into the colors that are available. I don't have Photoshop. I don't even have a computer that will run Photoshop. So, and Photoshop is hundreds of dollars. So I took a different approach though, and I want to show you how I do that. I took a different approach to generate this image. I'll just show it to you. So it's a little different, but it's very similar to the Ben Eater image, and it was done with entirely free software. So let me show you how I did that. Switch here. What I did was I wrote a little Python program I called convert image, and it's kind of like the one Ben did, but this does more than just generate the binary image. This does some of the image conversion for you. So the first thing I had to do was get the Goldien finch image, which I downloaded off the internet exactly the way Ben did, and it's this image here, Goldien-finch.jpg. This, by the way, is the PNG file that Ben saved from Photoshop when he was done. I've downloaded that off his website as well. Let's take a look at what this convert image program does. In Python, it's very common to define a bunch of functions, and then the actual main part of the program runs in an if block. And you say if underscore underscore name underscore underscore, which Pythonistas don't like to have to say that all the time. So what we say is dunder. So dunder name equals dunder main. And this dunder name is a built-in variable that Python has, and it will equal dunder main only when that file is being run as a program. If you import the file into another module, then dunder name will be something else, and so this code wouldn't run. And that allows you to have a piece of code that you can use as a library in other code, but can also be run as a command line. So the first thing I do is I use Python's argument parser to specify some arguments on the command line. I specify image file, which is going to be the name of the file that we want to convert. And I specify out file, which is the name that I'm going to write the binary file to. You can specify a height and a width, and I've defaulted the height to 75 pixels and the width to 100 pixels. I have a reason for that we're going to want different heights. So for example, you might want to only write 64 lines if you're connecting your VGA card to the Ben Eater 6502 computer, as he shows how to do in his videos. And you may want to change the width to be able to write outside of the visual display area of the card. And the reason for that, I'm going to show you in another special video that will be coming up soon. Then you can specify the size that you want to generate the binary to create. The reason you might want to do this is because some EEPROM readers, such as the one that Ben Eater uses, require that the binary image be the size of the EEPROM that you're writing to. Now, the one I'm using does not require that, so I'll be setting this to slightly bigger than the image size that's being created. And it's specified in kilobytes. So the default is 32 for 32 kilobytes, and that would be the right size image to write to a 32 kilobyte EEPROM. And then we parse the arguments. And then I use the excellent image library called Pillow that comes with Python. If you're going to install that on your computer, what you're going to want to do is you're going to want to install, in case of Ubuntu anyways, you're going to install a package called Python 3 Willow. So sudo apt install Python 3 Willow. And you can see I've already installed it, but that shows you how you would install how you would install that package. Let me back to the code. So this opens that image file in the Python imaging library, and that's going to do the heavy lifting for us in our conversion for this. So then all I do is I say with open args.out file. So that's going to be the path to the output file that we want. And we're going to specify that we're going to write to it and in binary mode, which means it's going to write individual bytes as we tell it to, as opposed to text mode, if you didn't have the B there, which would write in Unicode. And that would mess up our file. So we don't want that. And then as out file, this is called a context manager in Python. If you're not a Python programmer, this might be new to you. What this does is this makes it so that this file is closed automatically when we leave the block that's in the code for the with clause. And so this is the most common way nowadays to open a file, as opposed to just setting a variable equal to open. Then we call a function that I wrote called convert image. And let's go take a look at that function. So we passed convert image, the image that we created. The image that was created here. We pass it out file, which is the actual file handle for the output file. We pass it the binary size, that is the -s or -- size argument that we included. And we pass it the image size in terms of width and height. So that being passed in, we then call this function immediately. We get called getPalette. And getPalette gets an image that's going to be used in converting our high color image, our full color image, to 64 colors. So let's take a look at how that works. So what getPalette does is it, as it says there, creates an image that can be used as a palette. When we are going to be reducing the colors of our Goldie & Finch image in a few minutes, then we're going to want to reduce them to the palette, that is the colors used, to the 64 colors that the Ben Eater video card is capable of producing. So this is a list of all of those colors. The colors are in red, green, and blue. So the first 3 bytes are for the first color, the second 3 bytes for the second color, and so forth. And here I'm using 0, 0, 0 for black. And then the next image, the red is 0, the green is 0, but there's a little bit of blue. The next image, there's red is 0, green is 0, but there's a little more blue. And then there's red is 0, green is 0, and then bright blue. And then we continue on with red is 0, green is a little bit of green, and then no blue, then a little bit of green and a little bit of blue and a little bit of green and more blue and so forth. And this way I'm cycling through all possible combinations of 00, 55, AA, and FF to get all of the 64 colors that the Ben Eater video card can produce. The 0x here means that these are hexadecimal values. So this 55 would be 85 decimal, for example. But here I cycle through all of those colors. And then here I call, this is a list of all those byte values, and I convert it to a byte string. And a byte string in Python is a string consisting of values that are between 0 and 255 inclusive. So then I call a method on the image library, the Python image library, that will create an image from those byte strings. And I tell it that I'm creating a red, green, blue image. So this is going to be a full color image, but the image will only have the colors that are listed in the pixels above. I tell it that I want to make the image 64 pixels wide by 1 pixel tall, and then I pass it those palette bytes, which is a byte string with the image that's going to be created. So it creates that image, and then it's going to convert that image to a palletized image. So here I say the image named it palette, palette.convert to a palletized image. Colors equals 64, so that's how many colors to use. And then this input, this says palette, but it really should say palette type. And there's really only one palette type that you can use at the moment in the Python image library, and that is image.adaptive. And that palette type means take a look at the image and convert it to the 64 colors, in our case 64 colors that best match what's in the image. And then because we only used the 64 colors that the Ben Eater video card is capable of producing, this image will, of course, have just those colors. And a palletized image means that each pixel location in the image is going to be an integer value between 0 and 255, and that value is going to be an index to the palette itself, which has the colors. And so our palette is, of course, going to be the 64 colors we defined, and that is going to provide us with this palletized image, which is what we need. We then return that, we place that converted image back into the palette variable, and then we return the palette variable back to the caller, which was the call to get palette in the convert image function. So now we have an image that has just the palette colors we need. So let me just run this program a minute so that we can see what that does. So I'm going to write convert image, and we're going to be converting the Goldie and Finch, and we're going to convert it to, say, output.bin. And we're going to, and then we're going to want it to be a width of 100 and a height of 75, which are optional. We don't have to actually include that. And a size of, I'm going to go 10K because that's enough to, that's a big enough image to hold our picture. I'm sorry, not -H, it's -G, because -H means help, and so that's already taken, so I got to use -G. So there we go. So that converted the image, but all I want to do is I want to look at the so if you look here, after I get the palette image, I save it to palette.png. So let's take a look at palette.png. And here you can see it's a tiny little image. Well, of course, because it's just a few bytes, a few pixels. But if I blow it up this looks like these are many pixels, but this is one long pixel that's being stretched out. So here I have a row of pixels, and these are all the colors that the Ben Eater video card can reproduce, followed by a couple of rows of, or 3 rows of black. So that's creating our palette image. And then I'm going to call, now I'm calling on that image called palette, but remember we passed in the image that we're going to, that we read. So this is the Goldie and Finch image. And what I'm doing is I'm resizing that image to image size, which if you remember, it will pass in the width and the height. So that resizes it to the 100 by 75 and stores it back into the image variable. And then I call quantize. And this is what I needed the palette for. Here I'm telling it to quantize to 64 colors. I'm telling the palette to use, and there, before the palette was really palette type. This is saying this one wants a palette image. So this is the image that has the colors that we want the Goldie and Finch image to be converted to. And then we tell it how we want it dithered. A dithering is when you don't have a full color image. So what you do is you create a checkerboard of different colors that the eye will blend together into a single color that's as close as possible to the color that's actually in that region of space near that pixel. So there's really only one dithering algorithm that the image library supports, but it's a good one. It's called Floyd-Steinberg. I assume that that's based on a paper written by a couple of computer scientists named Floyd and Steinberg, but I haven't really looked into it. So this passes that image then back into our image variable. So now this image is quantized, and I've saved it as converted.png. So that's already been done because we did run that. So let's take a look at our converted.png. And it actually looks pretty good already. Let's compare it to the PNG that I downloaded from Ben Eater's website. And we can sort of flip between them. You'll notice it's a little squashed though. See that? It's a little squashed. And the reason it's squashed is because I didn't crop the image at all. So let's crop the image so that it's going to be not squishy like this. It's going to be the same shape as Ben Eater's. And we can do that as well with the program called Image Magic, which will be installed when you install the Pillow library, because the Pillow library makes use of it. But if you don't have it for some reason, you can install it with sudo apt install Image Magic, and it's magic with a K at the end. And you can see it's already been done. I already installed it, but that's how you would install it. Now, Image Magic comes with a program called Convert. So we can tell it that we want to convert our Goldie and Finch image. And you can tell it that you want it to crop it. And now we have to tell it how to crop it. So we're going to tell it that we want to crop it to, but first let's identify the image to see how big it is. So it also comes with a program called Identify. And you can tell it what image you want, and it tell you about the image. So this is telling me that it's 1024 by 671 pixels. So let's just go into Python and do a little math here. So 1024 by 671 is to divide that. Divide by 671. So the aspect ratio of that image is 1.526. Now we want a different aspect ratio. We want 100 divided by 75, which is 1.333. So we'll want to crop this image to a size that will be the same aspect ratio. So let's take a look at that. If we were to take a look at what width it needs to be, we have an image that's of 1024 by 761, or sorry, 1024 wide, and we want to crop it. We need to know what ratio to make that. Well, what we want to do is we want to crop it so that it's, let's see, 1.526 divided by 1.333. So what we need to do is we need to reduce its width by 1.145, right? So what we need to do is say, what's 1,024 divided by 1.145? And that's 894. So what we want is an image that's 894 pixels wide. And so let's just subtract that to find out what the difference is. So that's about 130 pixels. So what we want to do is make an image that's 194 pixels wide. And then we want to crop it evenly left and right. So what we're going to do is we're going to use this program called Convert, and we're going to convert the Goldie Finch, and we're going to convert that into by cropping it, and we're going to crop it to, what did we decide? 894 divided by 671, and then we have to tell it where to crop the image from. And so for that, you do a plus, and then you do the how far from the left, and then how far from the top. So from the left, we want to go half of 130, which is 65. And then from the top, we want it all the way from the top. So that's 0. And then we have to give it a name that we want. So we're going to call this cropped finch.jpg. So let's display cropped finch.jpg. So that looks good. So now let's rerun convert image.py. And only instead of using Goldie and Finch here, let's use cropped finch. And now let's display the converted. And let's display finch.png. This is the one from Ben Eater's website. Just blow that up. This one. Blow that up. Now let's switch between them. And there you go. You can see this is the Ben Eater one, and this is ours. It's not quite as nice. Like, I'll admit that Photoshop does a great job, but given that we're getting this for free, I kind of like it. So that's the image that I want to go with. So let's go back to the software now. Now that we've looked at and we've got a 16 color palletized, quantized image, and we saved that to converted.png. We looked at that. And now what I'm doing is I'm converting that palletized image back to a full color RGB image. Remember I told you that the palletized image, each of the pixels is an index into the palette. And so you can take that index and you can use it to read into the palette and then get the color from the palette. But you can also just have a pillow library do that for you. And by saying convert to RGB, it does all the math, it does all the conversions. And now we have RGB colors. We have an image that's full color image, but it's limited to colors that the Ben Eater video card can display. So next what I'm doing is I am going to create an image, the binary image. Let's say not a picture, but this is the binary image that's going to be written to the EEPROM. So for Y in range binary size times 8. So binary size, if you remember, was the size is the size of the hold on a second. All right. As I was saying, the binary size was the size in kilobytes that we want to create the binary image to be. If you take that size, so you take the binary size and you multiply it by 1,024, but then you remember that there's 128 addresses per scan line. So we want Y to be the number of scan lines. So we're taking that binary image, we multiply by 1,024 and we divide by 128, and that comes down to binary size times 8. 128 is the number of memory addresses per scan line. So we're going to say from X in range 128. Range is a function in Python that will run from 0 to the number just below the number you give it. So it'll be that many numbers starting with 0. So this range will run from 0 to 127, and the binary size will run from 0 to whatever number you gave times 8 minus 1. Then if we're inside the image area, then we want to compute the pixel's color value. So if X is less than the image size 0, so that was remember that we passed in a tuple, the first element of which, or the 0th element of which, is the width. And then we also, the second, or really the first, 0th and first, so the next element is the height. And so we're saying if X is smaller than the width and Y is smaller than the height, then we're in the image area. And what we're going to do is we're just going to call image.getPixel X, Y, and that will return the red, green, and blue values in a tuple. So here I go, I put in the red, green, and blue values. Now in the Ben Eater design, the low order 2 bits, or the 1 and 2's places, are blue. So those, you can see I just used directly. And what I'm doing is I'm taking that value, which remember is going to be either a 0, a 5, an AA, or an FF, and I divide it by 64, which is going to give me a 0, a 1, a 2, or a 3. And then I take the integer value of that, because like FF divided by 64 is almost 4. It's like 3.9 something. So this will round it down to 3. And same thing for the other values. This will round them to the value that we want. For the green, we do the exact same thing, except we multiply by 4, because the green is the 4's place and the 8's place. And then for the red, we do the same thing. We divide by 64, but then we take the integer value and we multiply by 16, because the red is in the 16 and 32's place, those 2 bits. It's important that you take you round first with int, and then you multiply by the value to put it in the place to make sure that you get the right value. If you do it the other way, it will mess it up. And then if we're not in the image area, then I set the color to 0, which is black. And then I convert the image. I do this a little differently than Ben. He's using Python 2 in his videos. I'm using Python 3. The correct way to convert a byte string to bytes is to call, or an integer to bytes is to call 2 bytes on it. And then you got to tell it how many bytes it's going to be. So we're just doing 1 byte at a time. So that's a 1. And then you have to tell it the endianness. And that is to say, let's say it was 2 bytes wide. Do I put the low order byte first or second? If it's first, that's called little endian, so I put little. If it's second, that's called big endian, and you'd put the word big in here. But it doesn't matter which one you do here, because we're only doing 1 byte. But I did little because that is in line with the byte order of Intel processors. Not that that matters. And then that's it. That's the end of the file. This then returns, once it's written all the bytes, all whatever number of K you told it to write. And then after it returns, then it closes out file and it's done. So we've seen that. Let's run it. We ran it on, so we already ran it on our cropped image. And so we already have a binary file. So we want to put that onto a chip, and I'm using a different programmer than Ben uses. I'm using one that looks like it looks like a lot like it's his, but it's this one called Tommy Prom. Mine looks like this. Let me move this out of the way. So mine looks like this one, and it's like Ben's. It uses a Arduino Nano, and then I have a pair of uh, serial chips and serial shift registers, I mean to say. And so that is what allows you to have enough address lines. You serial shift the address into here. And this is very similar to Ben Eaters, but it's wired slightly differently. It's got some improvements which are explained here in the Tommy Prom website at tomnisbet.github.io/TommyProm. And I really like it. It works well. It comes with sketches to do the programming. And it also comes with an Arduino sketch to test the hardware. So you can go bit by bit and you can test that you've wired everything up correctly and it's working. So let's put a chip in. And I've wired this up so that normally you would put a chip in this way in one of these zero insertion force sockets. But I've wired this one up to put it in so that the pin 1 is actually over here, not by the lever. And that's so that I can have the lever over here off the edge of the board so it doesn't interfere with the wires when you push the lever down. So now I've got that chip in. And let's look at how you program it using Tommy Prom. So Tommy Prom, you actually communicate with the Arduino using a terminal program, and the one I like to use is Minicom. And you have to tell Minicom what the device is that you're going to be communicating with. This is a knockoff Arduino Nano, so it's not at TTY ACM 0, it's at TTY USB 0. It could be at either. So you just want to type TTY and press tab and it'll show you your choices. If you don't give it a command and just press enter, it'll give you the Arduino sketch will return a list of instructions or a help menu. And what we want is the write instruction. So that's W. And you want to tell it where to write. And we're going to write to byte 0 on it. And then it says send the image file using X modem. So we're going to use Control AS, which brings up the send menu. And then we're going to down arrow to X modem to select that. And then we have to tell it where to find the file, the image file that we're going to send to the flash RAM. So I go to, and then I have to tell it it's in repos, circuits, BE6502/VGA, and that'll bring me to the directory. And then I'll arrow down to the output.bin file that we created with the convert image program. Press the space bar to highlight it and press enter, and it'll start sending the file. And you can see it sends pretty fast. It's 7, 8, 9, 10K. So there you go. So it's ready to put into our VGA chip. So let's do that. There's the VGA card. Put the image in there. Then we'll go to VLC and open capture device, video 2. And there's our image, created entirely with free software. So I hope you enjoy this video. If you did, I'd love it if you would like it and subscribe. And if you want to be alerted when I create new videos, be sure to click the bell. And I will talk to you again very soon.